Good morning. This is your Stats Sensei, Mr. Spensei, and this is the Death Packet Problems 11 through 20. The mean and standard deviation of a random sample of 7 baby orca whales, so in this case, n equals 7, was calculated as 430 pounds and 26.9 pounds, respectively. We got to be careful with that. Let's start labeling. Oh, there's the mean and there's my standard deviation. So my mean is 430. I should call that my X bar because it came from the sample. And I have a sample standard deviation of 26.9. Assuming all conditions for inference are met, which of the following is a 90% confidence interval for the mean weight of all baby orca whales? Well, my formula is X bar plus or minus T star S divided by square root of N. Well, X bar happens to be 430. We don't know T star yet. We'll come back to that. But that immediately gets rid of those first two. Then it asks for our standard deviation. Well, our standard deviation is 26.9, and we have a sample size of 7. So, well, everything else looks pretty good. But remember, to do the T star, I'm going to have to go inverse T. It's going to ask for my area, and my area is going to be 1 minus 0.90 divided by 2, and my degrees of freedom is going to be 7 minus 1. So please don't forget about the degrees of freedom. So second vars, inverse T, parenthesis, 1 minus 0.90, close parenthesis, divided by 2. Degrees of freedom, 7 minus 1. We end up with 1.943. The answer choice with that, E. So 11 is E. Number 12. The claim is made that the average IQ of students at Lake Wobegon High School is greater than 100. To test this, the principal gathers a simple random sample of 25 students and find their mean IQ is 102 with a standard deviation. What is the test statistic in performing this? Okay, so here we go. The formula, T equals X bar minus mu S divided by square root of N. Well, in this case, we have, they're telling us the mean is 100, so mu is 100. X bar, they're telling us that's 102. They're telling us we have a sample size of 25 and a sample standard deviation of 8.3. So plugging in 102 minus 100, then we have 8.3 divided by the square root of 25. All right, so that's wrong. This is close, but it's only the sample size that goes underneath, so that's wrong. This is plain wrong. This looks good. I like this one. And be careful, they use the degrees of freedom. Yeah, the degrees of freedom is 25 minus 1, but that's not what goes there. Just the sample size goes there because that's what the formula shows. All right? Number 13, a confidence interval estimate is determined from the summer earnings of a simple random sample of N students. All other things being equal, which of the following will result in a smaller margin of error? So let's go ahead and write down our formula. X bar plus or minus T star S divided by the square root of N. This is the margin of error. All right? As T star, which is the confidence level, goes up, ME goes up. As S goes up, ME goes up. As N goes up, ME goes down. Okay, so we want a small margin of error. Confidence level. Confidence level goes up, margin of error goes up. No. A larger sample standard deviation. Standard deviation goes up, margin of error goes up. No. A larger sample size. As sample size goes up, margin of error goes down. This is looking pretty good. And these have nothing to do with the problem, and we hate bias. Okay? So the answer is C. 14. To estimate the average cost of flowers for summer weddings in a certain region, a journalist selected a random sample of 15 weddings. So they're telling us N is 15 that were held in a state. A graph of the samples showed an approximately symmetric distribution with no outliers. Hey, they say we can use it. The sample mean and standard deviation were 734 and 102 respectively. So X bar is 734. 734. And S is 102. The journalist will create a 95% confidence interval to estimate the population mean. Have all conditions for inference been met? Well, let's take a look. 14. Random sample. Yay. We like that. Normality. We already said that they checked his distribution was normal with no outliers. So that's met. So the third one is N less than 10%. Question is, do you think there are more than 150 weddings? Because remember, N 10 times N, so 15 times 10 equals 150. Do you think there are more than 150 weddings in the state of Texas during the summer? And the answer is there's probably more than that every single day, probably more than that every single hour. So, yes, all the conditions have been met. Which of the following is true? It is helpful to examine your data before deciding on using a one-sided. That's cheating. Don't look at your data. Sounds like a good idea, but don't. All right. If the p-value is 0.05, the probability that the null hypothesis is correct is 0.05. No. The p-value is the probability of getting a test statistic this extreme given that the null is true. So if the null is true, there's a 5% chance we'd get a value like we did. So that's false. The larger the p-value, the more evidence there is against the null. No, smaller p-values has more evidence. If the p-value is small enough, we can conclude the alternative is true. That's possible. That sounds pretty good. We do not use sample statistics in stating the hypothesis. Oh my gosh, we have a problem. That's 100% true. So this is true all the time. So let's look back at this one. It sounded pretty good. If the p-value is small enough, we conclude the alternative is true. No, we don't conclude the alternative is true. We conclude that the null is false. All right? You're like, and then we're forced to accept the other. All right? So close, no cigar. The sample statistics are not used as stating the hypothesis. That's why we always use mu. We don't use X bar. Which of the following statements is a true statement? The p-value of a test is the probability of obtaining a result as extreme as or more extreme than the one obtained, assuming the null is true. I like that answer. 16A looks pretty good. If the p-value for the test is 0.043, the probability that the null is true is 0.043. No, the p-value is given that the null is true. So this has nothing to do with given. When the null hypothesis is rejected, it's because it's not true. No, sometimes we reject true nulls. We make a mistake. So that's false. All right. It just says that we have enough evidence to convict. It's kind of like we make a mistake in the court of law. Just because we convicted someone doesn't mean they really did it. We just think that they did. The greater the p-value, the greater the evidence. No, wrong. Smaller p-value, greater the evidence. A very large p-value provides convincing evidence. No, a very small p-value. All right, so the only answer is A. 17. Which of the following is true? If a population parameter is known, there's no reason to run a hypothesis test on that parameter. Yeah, if we know the true population, there's no reason to do a test. That sounds pretty good. Let's look at the rest of them, make sure that they're bad. The p-value can be negative or positive depending on, no, you can't have negative probabilities. Y'all all know that. The p-value is based on a specific test statistic, so it must be chosen before an experiment is conducted. No, that's alpha. Alpha is chosen before we start, not the p-value. The p-value is calculated based on the sample we get. If a p-value is larger than a specific value, alpha, then the data is statistically significant. No, if the p-value is smaller, that's true. But so if it's smaller, that's true, but it said larger, so this is false. The p-value is a probability calculated assuming that the alternative is true. Nope, assuming that the null is true. So that one's also false. So the only answer choice that was true was A. If you know the actual population parameter, we have no need of running the stupid test. Not that it's a stupid test. A linguist at a large university was studying the word length of papers submitted by students enrolled in the humanities program. From a random sample of 25 papers, the linguist counted the number of words used in each paper. The 95% confidence interval was calculated to be 20,995 to 22,905. These people had a lot to say. Assuming all conditions were met, which of the following is correct interpretation of the interval? Well, we are 95% confident that the mean word length for papers submitted by students in the sample is between, no, it's not in the sample. That's the problem. It's in the population. We know what the sample is. We're 100% sure that what they did. We just don't know what the population did. So that's false. We are 95% confident that the mean word length for all papers submitted by students in the humanities is between this close. Yeah. It's not for all papers though. How do I say this? This is not that bad. We'll leave it there for the moment. We're 95% confident the true population mean word length for all papers submitted by students is between this. That's pretty good. Let's keep going. See if there's any better. The probability is 0.95. We never talk about probability when we work on confidence intervals. As soon as I see that, it's like, I know that's wrong. Oh, the probability. Oh, that's wrong. For all students in humanities programs to submit papers, 95% are between this. No, we don't know that. It could be that we have a distribution that's shaped like this with no one in the middle. We could have someone who wrote a little bit and someone who wrote a lot. Well, then the average is in here, but we don't know what the actual papers are. All right. So we don't know what the actual papers are. We're talking about the mean, and it was the mean for all papers in the population is between this. And that's what I misread the first time. For all papers submitted by students in the humanities programs. In the humanities programs is the population, and we are 95% confident that the true mean word length lies within that interval for all humanities. Number 19, in certain regions of the country, elk can cause damage to agricultural crops by walking through the fields. One strategy to limit elk from crossing a field is to surround the field with a fence. Some elk, however, will still be able to bypass the fence. For a period of 1 month, the number of elk found crossing a sample of fields with a fence was recorded and used to construct a 95% confidence interval. All right, so almost 3 to about 4.5. Assume the conditions were inference met and verified. The interval 2.94 provide convincing effort for the following claims. All right. The mean number of elk to cross a field protected by fence is 4 per month. We don't know that. It doesn't provide convincing evidence of that exactly. We are confident, we're 95% confident that it's within that range. Could be somewhere as low as 3, could be as high as about 4.5. So let's see if we have a better answer choice. That's not horrible. Let's see if we have a better one. The mean number of elk to cross a field protected is 2 per month. That's obviously false because that lies outside the interval. The mean number of elk to cross all fields protected by fence is greater than 2 per month. Yeah, 2.94 is greater than 2 and 4.4 is greater. So I like that one better than A. So the mean number of elk to cross all fields protected fence is less than 2. Nope, definitely more than 2. The mean number of elk to cross all fields protected by fence is equal to 3.65. We don't know what it equals. We just know it's within a range. And so the best answer choice is that, hey, we know it's more than 2. It could be as much as about 3, could be as low as 2.94, could be as high as 4.4. So we believe that it's greater than 2. All right. Then number 20. A real estate agent claims that the mean sales price for homes in a city is 258,000. The contractor runs a check on a sample of 10 recent sales and notes the average sale was 245,000 with a standard deviation of 338,000. What is the test statistic in performing a hypothesis? Well, our formula is going to be T equals X bar minus mu S divided by the square root of N. All right. So they're claiming 258. So we know our mu is 258. The average sale was X bar is 245,000. Standard deviation of S is 38,000. And a sample size is 10. All right. So when we plug in, it's 245,000 minus 258,000 over 38,000 divided by the square root of 10. All right. This one's completely wrong because it used degrees of freedom. This is wrong because the square root's in the wrong spot. This is wrong. This one is our correct response. All right. I hope that helped and I hope to see you on the next one. Thank you for watching.